All right, hello everybody. Welcome back again. Today we're going to be doing section 5.3. This section is all about summations, which is kind of like adding up the terms of a sequence. Let me pull up the slides and let's get started. There we go. Okay, so let's look at an overview. So first, we're going to get some motivation. Then we're going to talk about what a summation is, and we're going to talk about some notation associated with summations. We're going to talk very briefly about series, which are essentially infinite summations, if you were adding up infinitely many terms. But we're just going to do a preview because you're going to explore series in great detail when you get into Calculus 2. Then we'll talk about summations. We'll do some examples, playing with the notation a little bit. Then we're going to get some properties of sums. And these are just properties that can help us compute finite summations a little bit easier in some senses. Then we'll finish up with some very brief, helpful summation formulas. And we'll actually see some of these formulas in the activity as well. All right. So let's start with the motivation. Very often, we want to add up the terms of a sequence and see what the result is. So for example, consider this sequence. This one should look a little bit familiar. 3, 0.1, 0.04, 0.001, 0.0005, 0.00009, 0.000002, and that's a sequence, right? It's a sequence, just a list of terms. Now, if we add up all those terms, then we get this sum right here. This is just adding them all up. And when we add them all up, we get 3.141592. And that's an approximation of the number pi. All right. So basically, adding up those terms gave us an approximation of pi. Now, more generally, if we have a finite sequence written like so, using the notation that we saw in section 5.1, we can see what happens when we add up all of those terms. So A1 plus A2 plus A3 plus dot 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 all the way up to AN. We can add those up, and we like to denote that with an S sub n. S sub n is what we call a sum, and the index n just indicates where to stop the summation. So if you look here at this notation for a minute, here is the sequence. The starting index is 1, and the final index is n in this case. So that number on the top is telling you where to stop. And in this case, it's telling you where to stop the summation. All right? So because these sequences can be really, really long. I mean, imagine a sequence where you have thousands or millions or trillions of digits, or I'm sorry, of terms, right? We don't want to have to write out each single term like that. And we don't want to have to write dot, dot, dot all the time. So we have a very handy notation to simplify our lives called summation notation or sigma notation. And it's this symbol right here. Let me zoom in a bit. There we go. So if we have a sum of, we'll say n terms, where the sum is going to go from I to n, we use this symbol right here to indicate A1 plus A2 plus A3 plus dot, 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 plus all the way up to AN, all right? So this symbol right here is equal to this summation that you see written out in expanded form there, all right? So this symbol, let me zoom back out, this little symbol here, that is the Greek uppercase letter sigma. It's basically a Greek letter S, which indicates a summation or suggests a summation. So we are adding things up, summing things up. I is typically a positive integer, usually it could be like 1, 2, 3, 4, 5. That's what the I is standing for, because here this A sub I is representing any arbitrary term indexed by the letter I, and that's called the index, much like we saw with sequences. You can use other letters for the index variable. Commonly used letters are J, K, and L. So you might see J's down here, or K's, or L's. In this case, in this symbol, 1 is the starting index, and n is the final index, where to stop the sum. All right. Okay, now let's preview the concept of a series really quick. So an infinite series, or just simply a series, is an infinite summation, and it's denoted with this symbol here. And notice here the sum keeps going, right? It's A1 plus A2 plus A3 plus dot dot dot, and it keeps going. There is no there's no final term in this case. There are infinitely many terms, and you're going to add all those terms up. And here, a sub I, that's going to be a sequence indexed by I. So basically the same idea as a summation, except it's infinite, all right? Now, these things play a critical role in calculus and beyond. So you want to get comfortable with this sigma notation and you want to get comfortable with sequences because we're going to be adding up the terms of those sequences. In the case of an infinite series, this is the notation we have. We also saw this before back in section 5.1. And a lot of times what we'll do in calculus 2 is we will have an infinite sequence, but we'll only add up a finite number of the terms. Maybe we'll add up n of them, for example. And if we do that, we produce what's called a partial sum. And that partial sum is just a finite summation. So that's exactly what we're looking at today. All right. So this is sometimes what we call a partial sum if your sequence happens to be an infinite sequence. All right. Now, what's really cool about this stuff, and I'm bummed that I can't go into all the details here, but if you're interested, I have a whole lecture series from Calc 2. You can check it out on my YouTube channel, and I go through all of this stuff in great detail in that lecture series. But it may surprise you to learn that when you add up infinitely many terms, the summation may actually produce a finite number. You may get a number by adding up infinitely many things. Yes, that's right. Other times you may get infinity or you may get negative infinity if you add up infinitely many terms. So that's also possible. Other times it may actually add up to nothing, meaning you keep adding up terms, infinitely many terms, but the terms never settle anywhere. They don't settle on a number. I'm sorry, the sum doesn't settle anywhere. It doesn't settle on a number. It doesn't settle at positive infinity. It doesn't settle at negative infinity. It just never settles. So that is what you're going to study in great detail in Calculus 2. It's really, really beautiful. Series are just fundamental to mathematics and science. So I'm excited for when you all get to that particular section of Calculus 2. Maybe I'll see you there. Okay, so let's go back to summations. We're just going to focus on finite summations in this course. And let's just get comfortable with the notation. Here's one that I want you to try on your own. And I want you to just write out each sum in expanded form, okay? So think about it for a minute. All right, you know what's coming next. Verbalize it. So say something out loud. Remember, it doesn't have to be to anybody. It could just be to yourself. Hopefully, it's to your peer who you're watching this with, or maybe your dog or cat. Just say something out loud to get your brain running, thinking about stuff. And now try to work it out on your own. We'll do it together in a minute. Just to give you a little hint, you're basically going to start by writing equals and then just write out all the terms of that sequence, but add them all up as you go along. Or just write out, the terms, but with pluses in between. Okay. All right, now let's do it together. Um, the first one is not too bad. Remember, I is the index. It's basically the variable of the sum. So everywhere you see an I, we're going to replace it with the index number, and that index number is going to increment. It's going to go up one at a time. So this would be like 1 over 1 plus 1 over 2 plus 1 over 3, 3 plus 1 over 4 plus, and we're going to go all the way up to 1 over n. In this case, n is the final index. So it is going to stop somewhere. It's going to stop wherever n is. But in this case, n could also be any number. It could be 3, it could be 10, it could be a million, but it stops somewhere. All right, now let's do this one. We've got the factorial function built in here. This is going to be 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial plus dot 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 plus n factorial. And once again, it stops, right? So we do have a finite final index, so it'll stop at n factorial. One thing I want to point out here is that this is not a sequence, right? This is not a sequence, this is a summation. What's happening is we have a sequence given by k factorial, and that sequence is going to determine the terms of our sum. But because we are adding up all of these terms, we don't have a sequence anymore. We have a sum or a summation, all right? So just bear that in mind that sequences and series are not the same thing. They are very different things. All right, here's just what I had written out a moment ago. Oh yeah, 1 over 1 simplifies to 1. So if you did that, great. Now let's go the opposite direction. And this is one that I want you to try on your own as well. So here I want you to express each of these sums using sigma notation. So what I've done here is I've actually given you a written out summation, and I want you to represent this summation using sigma notation. All right? Think about it for a minute. All right, now try to say something out loud, maybe a pattern that you notice about the terms of the sequences that could be used in these sums. All right. And now try to write it out. Get comfortable writing that sigma notation. If you want a tip or a hint, I usually do this and then that. I like to make a nice straight line and then kind of work down. Or you can just go like that, your choice. All right. Now let's look at it together. So one of the things I want to point out here is this is why we were studying sequences earlier and you had to do all those problems where you determined the formula for a sequence, right? Because these terms represent the terms of a sequence and we're adding them all up. So we need to be able to discern what pattern is at play here. So for this first one, I notice a couple of things. One, each one of these terms is going up by one. You see that? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I also notice there's an exponent, but that exponent doesn't change at all. So what that tells me is the sequence is basically, we'll say I squared. It's some index variable squared. Now to write that in sigma notation, we'll do this. I equals 1 to 12. 12 is actually the final index. See, there's 1, there's 12. And the formula in this case is I squared. So this is us representing this finite summation using sigma notation. And again, the notation is really, really nice because we don't want to have to write this out every time we want to refer to this sum. So this is one of those situations where the notation is really about convenience and conciseness. We want it to be concise, compact, and convenient so we can work with this object as its own object like so. Okay, now let's do the next one. This one should also look familiar. I know we saw this back in section 5.1. This looks like 1 over powers of 2. So maybe I'll write it like this. I'll use a different index variable this time. Maybe I'll use k. And k is going to start at 1. It's going to go all the way up to n. And we're going to have 1 over 2 to the k. All right. Now, if you remember, I gave a tip back in section 5.1 when we were working with sequences about checking to see if you have the right pattern. I'm going to give you all that same tip again today. Whenever you come up with a closed form for a series or a summation, you should write out a couple of the terms just to be sure that you got it right. So I'm going to do that right here. Let's do the one we just did. So 1 over 2 to the k. When k is 1, we get 1 over 2. When k is 2, we're going to get 1 over 4. When k is 3, we're going to get 1 over 8. And yeah, this is right. This looks right. So if you look back at this written out summation in expanded form, it's matching this form right here that I was getting from this closed form or this compact form of the sum. And that's about it. All right, let's see. How does it look? Oh, nice. I even used the right letters. Cool. Okay, so there it is written down in nice notation, just like that. All right, now let's talk about some properties of sums. There are a few properties of sums that can make computing these sums easier, and we're going to prove them right now. But to do that, we need to recall some properties of real numbers. These are properties that you learned way back in grade school, and we're just going to reference them again because we're going to use them to prove the following formulas. So first, there's commutativity of addition, meaning a plus b equals b plus a. You can move those terms around. You can commute those terms for sums, right? Then there's associativity. That basically means that you can associate a sum or a difference of three terms in different ways and you still preserve equality. The plus minus in this case is just standing for it could be all pluses or it could be all minuses. And the associativity still holds. It's just how you're grouping the sums or the differences, and you'll have equality there. And then there's the distributive property, distributivity. This is how products or factors distribute over sums and differences. So you can distribute the C to both of those terms, and you get AC plus BC or AC minus BC. That's the idea. All right, so these properties extend to any finite summations. And maybe if you take a discrete math course, you will prove these using finite summations. And we're going to use them to prove some properties of sums. A little note here that I have at the bottom. In some cases, these properties will also extend to infinite series in some cases, but not all of them. And that's where things get really interesting. So that's what you're going to talk about when you get to Calc 2. You're going to be like, wait a minute, when can I use these on an infinite summation? When am I allowed to commute the terms and have this equality? When am I allowed to do that? Because if it's finite, if there's only a finite number of terms, it holds. But if there's infinitely many terms, is it even possible for us to commute them and move them around? And if it is, do we still get the same result? It's an intriguing question. So Calc 2, it's fun stuff. All right, so here are the properties of sums that we're going to prove. There's this one first. Let's say we have two sequences, A sub I, B sub I, and a real number C. If we want to take the sum of a sum or difference of the terms of those sequences, we can split that into a sum or difference of sums. How many times can I say sum? Someone tell me, right? So here we're adding up AI and BI for every I. And what this is saying is you could split this up. You can basically add up all the AIs and then add up all the BIs and then add or subtract those results. That's what this first one says. The second one here really is just an extended form of the distributive law or the distributive property. It's saying if you want to add up these terms where it's C times AI, and that C is the same factor for each term, then you can factor the C out. You can factor the C all the way out of the sum and then just add up all the AIs and multiply the result by C. And again, that's really just distributivity, right? That's just this property being applied to a more general finite sum. And then there's this one. So this is a helpful one, but I know that students tend to struggle with this one the most. So I'm going to zoom in on it a little bit. Oh, let me get my other slides here. Hang on. There we go. There we go. Yeah, so look at number 3 here. It looks a lot more complicated than it is. We're going to see examples of it in a minute, and then we're going to prove it. So hopefully it lands by then. But here, let's say we're starting with this sum from I equals 1 to n of a sub I. Well, what we can do is we can essentially partition the sum into two or more individual summations. So here, I'm going to split this single sum into two sums by first adding up from 1 to m, and then I'm going to add up the remaining terms from n plus 1 to n. So this, basically adding from 1 to n, is the same as adding from 1 to m, and then adding from m plus 1 to n, as long as m and n are in this order, m is less than n. And that's the basic idea. And you can put that chop wherever you want. We're basically chopping, right? We're chopping this somewhere, adding up some of the terms, and then adding up the rest of the terms. You can put that chop wherever you want, all right? Okay, now let's see some examples. Zoom out. Here we go. So here's the first example of the first property or the first formula. Let's say we wanted to add up this sum right here and the terms have this form, k squared plus k. We can split that into two individual summations over the terms. So we could do the sum of k squared and then the sum of k's, just like that, like so. Here's an easy example of the distributive property in a more general form. If we wanted to add up the terms 5i, well, we could pull out the 5 to the front and just add up the terms I and then multiply the result by 5. Oh, you know what? A little note that I want to make here. This I is not the imaginary unit. So sorry if that's a little bit confusing, but this I here is not representing the imaginary unit. It's just representing an index variable. But most of the time, you can tell what it is by the context of the problem, right? If we did intend for this to represent the imaginary unit, then we would not use we would not use the index variable I. We would use something else like k or j or l or something like that. All right. Now, this last one down here, let me go back to these slides so I can zoom in for a minute. Okay, so this is the one where you're splitting the sum, okay? So let's say we wanted to add up ln of k, where k goes from 1 to 7, all right? We've got this finite sum here, and we're going to chop it into two pieces. So adding up these terms from 1 to 7 is the same thing as adding up the terms from 1 to 4, and then adding up the terms from 5 to 7. Does that make sense? That's the basic idea right there. Where you put that chop is really up to you, but this is like m. In fact, here, let me write this. This is like m, and this is m plus 1. That's 5 in this case, right? So now let me go back so you can wait. There we go, right? So in the previous one, this was what, 4, and this is 5. That's what's going on right there. All right, so that's the idea. That's the idea. You can put that split wherever you want. Now, let's prove these. The proofs are actually really straightforward. They're a really good exercise, even a good exercise for like an exam, because they just follow from these basic properties. So let's go through them one by one. All right. We're gonna do the first one, and we're gonna basically, uh, I'll say, distribute this sum over the terms, although that's not entirely accurate. We're gonna do the positive version, and the negative version follows from the same kind of an argument. So here we go. First, we're gonna write out this sum in expanded form. And if you notice, I've got a1 plus b1 plus a2 plus b2 plus dot 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 an minus 1 plus bn minus 1 plus an plus bn, right? Now, by the commutative property of addition, I can move all these terms around however I want. I can move this term way over here. Commutativity of addition lets you move those things around. So what I'm really going to do is I'm going to group all of the a terms together right here. And then I'm going to group all of the b terms together right here. And now that I've got those separately grouped, I'm just going to use sigma notation. So this expanded sum right here, that is just this written in sigma notation, right? It's the sum from I equals 1 to n of a sub I, boom. And then this right here, this is the sum from 1 to n of b sub I, boom. And that's what we were trying to prove. Here's our chain of equalities, right? So we've now shown that this is equal to this. Pretty cool stuff. The one for subtraction is basically the same. You just have to also use the distributive property. You basically group the a terms and the b terms together, and then you can factor things out, and it'll work out the same way. It's very similar. All right, now let's do the second property. This is just an extended version of the distributive property. Here we are, we're going to write out this, write out this sum in expanded form. There it is. Notice each one of these terms has a common factor of c. So we're going to factor c out of all of these terms, however many there are, n many. Doesn't matter as long as it's a finite number in this case. Well, we factored c out, and now we're left with this. C times a1 plus a2 plus a3 plus dot 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 plus an minus 1 plus an. And now we're just going to write this in sigma notation, and we're done. There it is. So this is equal to this. Okay, now the last one. So here you'll really be able to see where that chop is, where that split occurs, right? So here we have a sum of a sub I from I equals 1 to n. We're going to write it out in expanded form. I'm going to put the index m somewhere in there. It really doesn't matter where it is, but it's in there somewhere. And that's why you'll notice these indices are going 1, 2, dot, 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 m minus 1, m, m plus 1, dot, 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 n minus 1, n. And remember here, m can be any number that is less than n. So, if n is like a million, this m could be 1,000, and then this would be 1,000 plus 1, right? Or 1,001. And you can make the chop right there. You could chop this summation into two pieces from 1 to m, and then from m plus 1 to n. That's what's going on. So we're going to chop it right there. And then we're just going to write this using sigma notation. There it is. And then we have that chop. We're going to write this using sigma notation. And remember, this is the starting index, m plus 1. So that's why that's appearing down here. And then the final index is n. And that's why that's appearing right there. And that's it. So that's how you can split it up. All right. Now, the next slide, I have a bunch of helpful summation formulas. I'll talk a little bit about these. We'll play around with them, and then you'll get some more practice with them on the activity. But let's just go through them first. So there's this one. If you wanted to add up the number c from k equals 1 to n, then what's happening is the sequence is just a constant sequence. It's just the numbers c, 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 however many times is indicated by this n up here. It's going from 1 to n. So if we're just adding up c n times, that means we're repeatedly adding the number c n times. Well, that's just multiplication, right? So that's why we're getting n times c. So if you have a constant sequence like that, and you write it, or like this, I should say, and you add up the terms of that constant sequence, you're really just doing multiplication. That's what's going on there. So this is equal to n times c. Okay, now let's check out the next one. You know what? I think I want to zoom in on these. Let me do this real quick. Let me zoom in a bit. There we go. Okay, let's look at this one. So this is a special one. This is one where there is an index variable that's changing in our sequence. So here we're adding up k, where k goes from 1 to n. We kind of saw this earlier, right? It's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus dot, 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 all the way up to n. And this is a really helpful formula because it gives you a closed form of this sum. So in other words, if you wanted to add up the numbers from 1 to n, it turns out this formula gives you that result. N times n plus 1 over 2. Pretty cool stuff. We're not going to prove these, but we will explore them in the activity associated with this. So adding up the first n positive integers, you can jump right to the final result by using this formula, n times n plus 1 over 2. All right? Okay, next, you might notice a pattern here, k squared, k cubed. The next formula is for when we add up the first n squares, or I should say the first n squares of the positive integers. So here, k is going to go from 1 to n. We're going to get 1 squared plus 2 squared plus 3 squared plus 4 squared, on and on, until we get to n squared. And a closed form for that sum is this: n times n plus 1 times 2n plus 1 all over 6. And that's this right here. And again, the beauty of these formulas is that this means you can jump straight from here to here, or you can jump straight from here to here. You just need to know what the final index is, and you're done. That's it. Now let's do the sum of the first n cubes. So 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed, all the way up to n cubed. It's actually this formula, which is very similar to this formula. It's in fact, it is this formula squared, which is pretty interesting, right? Okay, now, before we mess around with these for a minute, let me give a little bit of word of advice. Some instructors will require you to memorize these formulas because they do show up again when you get into Calculus 2, or I'm sorry, Calculus 1, and you talk about what are called Riemann sums. You'll actually see an example of a Riemann sum on the homework, but just be aware that some instructors will require you to learn these formulas and memorize these formulas. I do not require you to memorize these formulas because, in my experience, they are helpful for proving a couple of things and doing a lot of really difficult, tedious Riemann sum calculations. But the moment you get the integral, you can kind of dispense with them. So just be aware that you may have to memorize these in the future. But if you're taking my section of this course, I will not require you to memorize these. All right? Okay, now let's do some examples. And I want you to try these on your own. Don't worry, you'll be able to do it. I want you to try to find the value of this sum, S sub 96, which is the sum from I equals 1 to 96 of 4i, okay? So think about it for a second. Like, try to make sense of those symbols. And then say something out loud to give your brain that feedback. Maybe, oh, what's a property that you see you could use? All right, now try to work it out on your own. Use those properties of sums that we learned just a few minutes ago, and then use those helpful summation formulas. Okay. Now let's do it together. You know what? I'm going to pull up the next slide just to save a little bit of time here. So we can use property two above and the helpful formula number two to expand this in this way. So let me walk you through the steps. This is just what we were given, but remember by that one property, we can factor out the constant factor of four and put it in front of the sum. Now what we have here is the sum of the first six positive integers. And we have a formula for that. It's n times n plus 1 over 2. In this case, there's a typo right there. That should say 96. 96 right there. In this case, n is equal to 96. So n is equal to 96 in this case. Oh, where is it? N equals 96. So what is n times n plus 1 over 2? It's 96 times 96 plus 1 divided by 2. Now we can use all sorts of arithmetic manipulations that we want. We just got to massage this. If these numbers are large enough, you can basically just use a calculator. But I like to try to simplify things before I turn to a calculator. Here's the first thing I notice. 96 is an even number, so it's divisible by 2. 96 divided by 2 is 48. And now we have this product times 4. And for this, if I wanted to play around, I would do it by hand. Or if I wanted to be done with it, I would just use a calculator or Desmos or Wolfram Mathematica or something like that. But 48 times 97 times 4 is 18,624. All right. Now, again, what's cool about this is we just found the result when you add up these 96 terms. It's 96 terms. So if you think about what this is in expanded form, it's this. It's 4 plus 8 plus, oh my gosh, I can't do this math. What is it? 1, 2, plus 12, plus 16, plus 20, plus dot, 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 all the way up until you get plus 4 times 96. All right, that's what we just computed. And that sum is equal to 18,624. Pretty cool. All right, here's another one. Try this one on your own. Think about it for a minute. Take a look at the sum. Wait, where is it? There's the thinker. Think about it for a minute. Right? Now say something out loud, verbalize it, maybe what properties you can use. Right? And now work it out on your own and we'll do it together. Use those properties, use those summation formulas. Right. Here we go. This one is a little more complicated. So maybe, let me see, maybe I'll zoom in on some of these pieces. One second here. Here we go. All right. So the very first thing we can do is we can use those properties. We're adding up these or this expression from k equals 1 to 23. So the very, very first thing I'm going to do is use all of those properties. I'm going to split this into three separate sums. I'm going to factor out constant multiples. And here's what we get. So this is going to be equal to this sum minus 4 times this sum plus this sum. And now the reason that I'm doing that is because each one of these sums, let me highlight them. This one, and this one. In fact, you know what? Let me change the colors for these just so I can match them up. Do that, and then we'll do this. There we go. So each one of those sums has a closed form, just a concise, compact form, right? In each one of the cases, n is equal to 23, but we have a formula for it. So for example, here's what that blue sum is equal to, right? We're adding up those squares, okay? So what we've got is, ah, can't deal with it. Got to do it all over. Okay, here we go. Hold on, hold on. There we go. So in this case, n is 23. So we've got n times n plus 1 times 2n plus 1 all over 6. There's that one. Okay, now let's look at the red one here. It's 4 times this. There you go. Right? And again, n is 23. So we've got n times n plus 1 over 2. And then the last one, this one right over here, which I highlighted in pink, this one, again, n is 23, and we're just adding up the number 5 23 times, which means we're doing 23 times 5, or we're doing 5 23 times, right? So it's just 23 times 5. And here's n, and here's c in that case, if you want to look back at the more general formula. At this point, it's all just massage, 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 get all the kinks out, uh, simplify things, cancel common factors. I recommend practicing these skills and just simplifying as much as you can before going to a calculator. Remember, we have mathematical technology, even just a calculator, that could easily do all of this instantaneously, but it behooves you to practice these skills a little bit, right? Look for common factors, cancel common factors, simplify these things until it gets to a point where it's like, I've just got to do a product of some really big numbers. I'll just use a calculator. So here's an example, right? I simplified this numerator to this, and then sticking with this, look, I've got 24 divided by 6. I can do that in my head. It's 4, right? So this 6 goes away, and then what I'm left with is 4. Much simpler, right? That's easy to plug into a calculator. I'm saving myself the work. Here, same thing. This is going to simplify to 23 times 24 over 2. Again, 24 over 2 is 12. So I might as well do that simplification. 23 times 5, well, 20 times 5 is 100. And then 3 times 5 is 15. So 23 times 5 is 115. There you go. And now you're just adding up all the results. So here's a situation where if I wanted to, I might play around with it a bit more to simplify things, or I may just go to a calculator and add it all up, and that's what we get. Yeah, yeah. Actually, here it looks like, oh, check this out. Let me show you this little trick since I have it on the slides here. I did do some more manual simplification. So let me point this out because this is kind of cool. Take a look at these two terms here and here. Those two terms have common factors. They've got a couple of common factors. Notice they have 23 times 4. They both share a common factor of 23 times 4. So we can factor that out of both of these terms, just like we talked about before. So I'm going to take this, and I'm going to factor it out. And then what'll be left over is 47 minus 12. Let me write that out. I'm just going to kind of pull this off to the side for a minute. We're going to get 4 times 23 times 47 minus 12. Well, what's 47 minus 12 equal to? 35. There it is. So I was able to simplify these two terms into this single term just by factoring something, right? And now here, might as well just go to a calculator and we get 3,335. So this is the reason why I say it's fun to practice those things, and it can help you to practice those things because it helps you reinforce what you know about the structure of these expressions. A lot of this stuff is structural. Okay, let's do one more. And again, I want you to try this one on your own. So, first thing, think about it for a minute, look at it, ponder it. Oop, I have a typo here as well. Um, maybe, yeah, that shouldn't be there. We'll just say S equals that. So pretend you don't see that. I'll mark it out in each one of the slides. Okay, now say something out loud. What is something you notice about the sum that you're being asked to compute? Okay. All right, now work it out. Do that calculation, use those properties of sums, use those helpful sum formulas, and we'll do it together in a moment. All right. Okay, here we go. So, a couple of things I noticed right off the bat. First thing, the index is not starting at 1, it's starting at 6. The stopping index is 20. This looks like I cubed, so I can use that sum of cubes formula, or I mean the sum of the first n cubes summation formula. There's a common factor of 2 that I could pull out, but the main thing here is the index does not start at 1. And that's an important point because if the index does not start at 1, then we can't use those helpful summation formulas. And I say that right here. Let me cross this S6 out again because that really shouldn't be there. Um, yeah, so I mentioned this right here. The index starts at 6 instead of 1, so we can't use that formula that we would want to, the one that just lets us like add up all those things and get a closed form. But what we're gonna do is we're gonna use that property number 3, the one that lets us split a sum. This is a perfect example of where that can really help simplify things. So here's the clever bit that we're gonna do. Um, we're gonna take this sum that we were given, and we're gonna write it as this sum, which starts at the index 1 and goes to 20. But then what we're gonna do is we're gonna subtract the terms from 1 to 5. All right. All right, that's what we're going to do. So in particular, we're saying, hey, add up all the terms from 1 to 20, but then take away the first 5 terms. And if I add all the terms from 1 to 20 and then take away the first 5, that's going to be the same as adding up all the terms from 6 to 20. Maybe if you want to see like a perfect alignment of the structure, you could take this and add it to both sides of this equation, and then you would have this plus this equals that, which is the form of that property that we had earlier, splitting the sum, okay? So yeah, to put it succinctly, if you want to calculate the sum from 6 to 20, do the sum from 1 to 20, and then subtract off the first 5 terms. That's what we're going to do. The beauty of this method is that both of these summations start at index 1. So with these, we can use one of those closed formulas. The closed formula for the sum of the first cubes after we factor out that 2, of course. So let's see that. Here we go. And that should not say 6. There we go. Okay, so here we go. We're going to use that formula outright. Let me highlight what's going on. So we're looking at this sum right here. Oh, wait a second. Wait a second. Ooh, ooh, ooh. Hang on, hang on. Do I have this? I think I'm missing my 2's. Hang on. Just give me a moment to look at this for a second. All right. Okay. Sorry about that. I had a different formula or a different sum that I was computing, and had to modify it. So I wanted to pause and then fix that error before I went on because it changed the entire calculation. So let me start over explaining this one here. Sorry about that. Here's our sum. We're going to write it in this form like we did before. Here I'm factoring out the 2's. There you go, factoring out the 2's. And now what I can do is I can use those helpful sum formulas, in particular the one for the sum of the first n cubes, right? So let me highlight the first one here, this one right here, and I'll show you some other algebraic tricks, which are kind of nice, or maybe arithmetic tricks. That one is this one right here, from 1 to 20, and then the other one is going to be this one right here, which is 1 to 5. There we go. There you go. So again, in this case, n is 20, so that's why we have n plus 1. Here, n is 5, and that's why we have 5 times 5 plus 1, just like that. Now, again, we're going to simplify things before we go straight to a calculator. Nice things that I can see here, 20 over 2 is 10. And then 20 plus 1 is 21. Here, 5 plus 1 is 6, and 6 divided by 2 is 3. So this just becomes 5 times 3. And now here's a fun exercise. This is the expression we're trying to compute at this point. But there are some common factors. There's some common factors in these terms. There's 2 terms here, right? There's 1, 2, and there's common factors. But they might be a little bit hidden. So here's what I'm going to do. I'm going to be a little bit clever. I'm going to, where is it? I'm going to take this 10 and I'm going to read it as 5 times 2. Okay. And then I'm going to take that 5 times 2 and I'm going to take the 2 and multiply 21. And that's going to give me 42. And the reason I'm doing that is because now I have 5 times 3 and 5 times 42 and 5 times 3. So I'm getting all these common factors. Of course, there's a common factor of 2 to both. So now I'm going to factor out everything I can, everything common. So I'm going to factor out 2 times 5 squared from both of these terms, and I get 2 times 5 squared. What remains? 42 squared and 3 squared, just like that. 42 squared and 3 squared. There we go. Now here is about the time I would probably go to a calculator because that one I can't do in my head. Well, I shouldn't say that. I could do it in my head, but Not right now. So I'm going to get 1,764 minus 9. That's 1,755. And now I'm just doing 50 times 1,755, which ends up being this right here. And that's the idea, all right? So using those formulas, using those properties, using some arithmetic skills that we've built up over the course, and then probably using a computational tool to help us get the final answer. All right? Okay, on that note, let's play. So thank you for bearing with me on that one. Sorry for the errors. I fixed them on the slides, so you'll be able to look at those later, and it should look better when you're watching the video. That ends this section. We've only got one more section in chapter 5. That's the section on the binomial theorem. So I will see you next time when we talk about the binomial theorem. And thank you for watching. Have a good one, everybody.